Well, welcome to this final session and welcome to Roger Penrose, whom I'm going to talk to for the next half hour or so. Roger, when you think of your background, your family, there were artists, there was a chess grandmaster, there was a geneticist, mathematician. Do you feel you were fed by that multivariate academic atmosphere?
I think that's undoubtedly true. I mean, my father worked in human genetics. Both my parents were medically trained, and actually they assumed that I was going to be, of me and my two brothers, I was the one they decided was going to follow them in the medical profession. And I believed this myself right up until I think I was in in the second year, I think, at school, and we had to decide what in the last 2 years, what subjects we would do. And each one had to walk up and talk to the headmaster. And I remember as I was walking up to talk to the headmaster, I was going to be a doctor because that's, it was sort of established I would follow my parents' professions. And then he said, well, what subjects do you want to do in your final 2 years? And I said, I'd like to do biology, chemistry, and mathematics. And he said, no, you can't do that combination. If you want to do mathematics, you can't do biology. If you want to do biology, you can't do mathematics. Make your choice. And so I said, well, mathematics, physics, and chemistry. And that was because I didn't want to lose the maths. I realized there was my medical career going down the drain. And when I got home, both my parents were really annoyed with me because that was the end of my. Actually, they won in the end because I had a little sister who was eventually became a doctor herself and married one as well. So they really won in the end, but not with me.
Was this something that mathematics was a thing you had to keep a grip on?
I think it was I just fell in love with it. No, I certainly had a great fondness for mathematics from quite early on. Certainly when I was 9 or something like that. I can't remember the exact age, probably earlier. But I hadn't thought of that as a career. That really came gradually. First of all, with this, when my parents had been very disappointed with it, I ditched biology. Of course, these days you could do biology and mathematics, but in those days it was very much more restricted what one's allowed to do. But later on, when I decided to do mathematics, just mathematics at University College for my undergraduate degree, my father was again very angry about that. He considered that people who just did mathematics were rather strange characters, you see. And he thought I could do other things as well as maths, so I should be more broad in what I did. But I was very determined. And I think, yes, my father had one of the lecturers, a man by the name of Kesselman, who was he was an extremely good lecturer. And I didn't know that at the time because I wasn't there yet. But he made up a special lot of test questions. I think there were 6 or 12, I can't remember quite. And they were very sort of unusual that I would never have come across before. I respected him a lot for taking all this trouble. But anyway, he made these questions up and he gave them to me and said, well, you can take as long as you like. And if you only do 1 or 2, that's fine. But then he came back later in the day and I'd done all of them. So he was quite impressed by that. So I think that was what converted my father. He allowed me to do mathematics.
Yeah. Did the melee, it wasn't a melee, it was really an extremely well-ordered household among your relations and their friends?
Well-ordered slightly worries me when you that. It was a bit chaotic, but go on, yes.
I mean, did you get something from the artist side and from the other side and that side?
Yes, I think definitely from the artist side too.
Yeah.
Because my father was a very good artist, and he was one of 4 brothers, all of whom were, well, one of them particularly distinguished as an artist. That was Roland, who was a younger brother of his. And Roland became a big figure in the art world and surrealism, and he was familiar with all the people, with Picasso and Max Ernst and various people like that. And he then became a big figure in surrealist art in Britain. But
There's a plaque to him I pass most days.
oh, yes, I see. Well, yes, but you see, my father's father was a professional artist. He was very skilled, extremely skilled. But he did sort of very religious pictures. He was a Quaker, and my father was also a Quaker, but not sort of religious Quaker. He was more moral Quaker, you might say. And he used to go sketching, and I sometimes went with him sketching. He was very good at sort of doing pen and ink, I think was his particular skill he had. But I did more wild things, which were not necessarily realistic, and I don't think he approved of that very much.
But the idea of drawing and drawing as part of the intellectual, of the life you led, was just there from the start.
That was very much true in my case. I don't think my brothers were so much on that side. My sister picked up on it rather, but certainly my father's side, yes. And I got a lot from him on the artistic side. I think that's true.
When you are at school, you said that you realized your mind worked in an unusual way. I'm quoting now. I thought maybe when I go to university, I'll find people who think like me, but it wasn't like that at all. When I would talk to someone about an idea, I found myself not understanding a word that they were saying. That's quite a strong remark, Roger.
Well, it was sort of that I could pick up the gist of what they were saying without really understanding the words. It was quite strange in a way. Obviously, that thought processes were very different. So when I went to university, I found that, in fact, people thought very differently from me on the whole. I think it was mainly the visual, non-visual divide, which is quite a significant one. I mean, there are lots of other differences, but primarily that one. There are people who tend to think visually and those who tend not to think visually. And I was very much on the visual side. I seem to remember when I was at university, there were only one or two people who thought very much on the visual side, one of whom was me, or well, two or three, I guess. I can remember one other particularly. But I mean, other people could do it, but that wasn't their primary way of thinking. So it was a lot. The variation in ways people thought about things was quite striking. And as I say, when somebody might be talking to me, describe some idea, and I wouldn't really follow the actual words or sentences in any detail, I'd pick up the gist of what was being said and maybe come to the conclusion that was required at the end, but not exactly following the details of what was being said to me.
Did that stay with you, or did it resolve itself in some way?
I think it stayed with me. I think, no, I think it's very true. Well, I think it was true in relativity. I think that was a distinctive feature, that I thought about the subject very much in pictures and how light rays behave and things like that, and rather than the equations. I mean, I could do the equations when needed, although even then I would have a very different way of looking at equations often. And this came about when I was a graduate student mainly, and I was supposed to be doing algebraic geometry under Hodge, William Hodge, who was a very distinguished algebraic geometer. But I don't think he was very visual in his thinking, but he gave lectures on differential geometry, and he was sort of equations all over the board, and he was a very disorganized lecturer. And I had a great deal of trouble following in detail what these things meant. And so I developed this notation where instead of having symbols, you see in the subject of differential geometry or relativity theory, you have symbols with lots of indices, and then indices at the top and indices at the bottom. And then you have to see which letter here corresponds to which letter over there. And that was much too complicated for me. So I just draw a line connecting these things. And I developed this diagrammatic way of expressing these equations. And it wasn't the way anybody else did it, but it was very helpful to me in trying to sort out the problem that he'd set me.
Did it work?
Yes, it worked. I didn't solve the problem because the problem didn't have a solution in the form that one expected. This was a striking thing, because I used this method to show that there was no solution to this problem in the most obvious way. You'd expect you're trying to construct something. You had two objects and you had to combine them together to make a third object. I won't go into the details of that. And these were very complicated algebraic expressions. The geometry is very simple. You're looking for the intersection of two geometrical figures. And that was clear to visualize what we're trying to do. But to do it algebraically, it was very, very complicated. And in order to do this, I developed this notation. And I had these pictures with lines all over the place. And I remember showing them to Roger, my supervisor. And I don't think he followed what I was doing. He thought about it very differently. And so I at that point, I didn't show anybody for a long time. But no, it helped me sorting out this problem and to see that there was no solution in the most direct way, and you had to go indirectly to find a solution. But,
when you were still a graduate student, you developed the Penrose triangle. What was that, and why was it such a breakthrough? Not a breakthrough. Why would it please you so much?
Well, this was a complete digression from what I was doing. You see, I was at Cambridge at the time. I think it was in my second year, and there was a conference. The International Congress of Mathematicians was taking place in Amsterdam, in the Netherlands. And I and a colleague decided we'd go to this conference. And I remember I was finding a lot of it was very mysterious and difficult to understand, but there were lectures by Herman Weil, I remember, which was very impressive and so on. And I think I was getting on a tram at one point, and one of my lecturers, Sean Wiley, who taught me about algebraic topology, and he had in his hand a catalogue. And this was a catalogue of an exhibition that was being held in one of the museums in Amsterdam. And he said, you might be interested in this. It had this strange picture on the catalogue with these, now a famous picture, one of these, it's called Night and Day, one of the Escher pictures with birds flying, and one way it's into the night and the other way it's into the day. And the gaps between the birds become the birds on the other side. And it's very clever. And I'd never seen anything like that before. And so I went to this exhibition. It was in the Van Gogh Museum. And they had a special room full of these Escher pictures, as they thought that mathematicians would be interested in that. Escher was not famous at all at that time. And I was absolutely stunned by these things, most particularly one called Relativity, which is a picture where the force of gravity was in 3 different directions and people were walking upstairs and at right angles to each other and that sort of thing. And it was utterly fascinating. And I went away thinking that I hadn't quite seen something of the nature which I had in mind, which is a picture which was locally consistent, but as a whole, inconsistent, because there's a sort of ambiguity in the local picture about how far away it was from you. And I drew pictures with bridges and rivers and roads going different ways. And then I simplified it to this thing that people refer to now as the tribar, 3 rods, each at right angles to each other. But you can't construct locally, you can, you see. So you can have a local picture and it makes sense locally. But since the distance away from you gets inconsistent at some point, then it's an impossible figure. And I remember showing my father, and he showed it to his colleagues, and they all felt very ill looking at these things. And he then developed that into impossible buildings. He had one he called an impossible college, I remember. And then he produced a staircase which went round and round and round. And we then wrote a paper on this.
You and your father?
Sorry?
You and your father?
Yes, my father and I, that's right. And we wrote a paper on this, and we couldn't decide what the subject was and where do we send it, you see. Well, my father said, well, I happen to know the editor of the British Journal of Psychology, so I'm sure he will accept it. So we decided the subject was psychology and sent this paper to the British Journal of Psychology. It was duly accepted. And then we sent a copy to Escher. We'd acknowledged the catalogue to the museum, so the influence that Escher had. In the meantime, Escher had produced a picture of Belvedere, which does illustrate the same thing. But then he picked up on this and he developed the staircase into the one called ascending and descending. and the triangle into the thing called waterfall.
You said of the triangle, its impossibility in its purest form. Why did that attract you? And why did you use the word purest?
Well, you see, it's really, it's not, there's no kind of elaborations to it. I mean, it really is just the impossibility. That's what I meant. What I didn't know was that there was this Swedish artist called Oscar Rottisvard who'd previously drawn a very similar thing with cubes going around like that, which I didn't know about. And there are old pictures you can find. There's a Bruegel picture called The Gallows. I think it's called a jackdaw on the gallows, is it? I'm not sure if it's jackdaw. And it's joined up differently in the top and the bottom. So it's quite deliberately. I mean, some people thought, oh, he's made a mistake. No, he didn't. It was absolutely deliberate. You could see that.
Did this attract you partly because of your interest in drawing, as well as your interest in the pure impossibilities?
I think so. Well, you see, we did other things together. That wasn't actually the first thing we did together. The first thing, as far as I can recall, was we were on a train going to Switzerland, where my mother's mother, my grandmother on my mother's side, lived, and we were going to visit her. And my father came up and he said, well, look, perhaps you could help me developing an idea, because there was the question is whether you could build a machine which would reproduce itself. And the great mathematician von Neumann had proved some theorem that with some several thousands or millions of pieces, you could make this machine which would copy itself. My father he knew about this, but he wasn't very pleased with it. He thought, well, you know, life has got come about from something simple. So there must be some simple thing which will reproduce itself. He suggested using something with gadgets which would copy themselves. And so
you had that to solve on the train on the way to Switzerland, did it?
On the night, it was a night train, you see, and so we had bunk beds or something. And I remember I produced my solution and he produced his solution. His was better than mine. I think he appreciated mine, but I think he thought his was better. I think it was better. So we then wrote an article for Nature, which got published between us, which was called Self-Reproducing Analog or something. And it had these two little pieces, and you have them in a track, and you shake the track, and they just hit each other, and they don't combine. But if you link two together, and you can link them two ways, this way or this way. If you link them this way, then two other pairs will link up the same way. If you link them this way, then other pairs will link up that way the same way. So it was a very simple, very, very simple example of something which you could imagine some molecules doing something similar. So if life could begin with something extremely simple, not these complicated, vastly complicated things that von Neumann had introduced. So I thought the idea was a very good one, not in detail, anything like chemistry or what life would be like. Well, then my father then went on and developed much more complicated things he was trying to model DNA and that sort of thing. So he got a little bit, I think, too far into making these. He had a little workshop in the back garden, and he would plug away with his pedals jigsaw and make dozens and dozens of these little machines.
In 1964, you were said to have, I'm quoting, revolutionized the mathematical tools that we use to analyze properties of space-time. That's quite a mouthful. It must have been quite a... It's quite... So can you unravel that for us?
I think it's what you were saying earlier. You see, I was thinking about the subject differently from most people. You see, most people at that time, when I said that time, this was a little bit before 1964, it was when the quasars were being seen, and they were suggested that they were gravitational collapse, sort of bodies coming together and producing who knows what, and producing these very bright signals, which became known as quasars, which are extremely bright sources in the radio signals. And they were very puzzling to people. But you see, the two ways people might think about general relativity at the time were either the mathematicians who were just trying to solve the equations. And you could only solve the equations in a very simple symmetrical, or had some very simple characteristic which you could use as as a gadget to allow you to find exact solutions of the equations. I could do that sort of thing, but I wasn't a particular expert at it. The other thing people might do was put things on computers. At that time, they hadn't got very far with how modeling things that we now call black holes. But I was thinking about it in a different way, which was much more geometrical. So I had this way of trying to visualize what was going on all the time and how light rays behaved. And it was very much my style of thinking.
Were you making drawings?
Oh, absolutely. Yes, drawings all the time. But it was how light rays focus. That was the main point. And there's a really close analogy. Well, I'm glad I did physics at school, because you see, one of the things we did at school was play with optical benches. And you have an optical bench and you have these lenses and you have them different distances and you see how they focus light and all that. And then you can have pure lenses, which are anastigmatic. So the focusing is the same in all directions. Or you can have astigmatism, where the focusing in one direction is different from the focusing in the other direction. And a purely astigmatic lens is when it's completely positive in one direction and negative in the other direction. And the curvature due to pure gravity is of that kind. So I could understand how the focusing of light rays behaved from having this experience in doing physics at school with playing with optical benches. So that was useful to me. So that's not just drawing pictures, that was having some idea of what the physics was involved. So you're not lenses now, but the kind of lens that gravity acts, how it acts on light rays, and the purely positive focusing lens, convex lens, which is positive focusing, is what matter does.
Can I just come back to the quotation, though, that somebody, another scientist said to me, the two words revolutionized the mathematical tools. Now, if you could dwell on those two, revolutionizing tools, for a minute or two, I'd be very grateful.
It's a hard question to answer. It's just that people weren't thinking that way. As I say, they were either looking at special solutions, which didn't tell you much about the general case. You see, there was this model of collapse to a black hole, as we would now call it, due to Oppenheimer and Snyder, which was put forward in 1939, just before the Second World War. But that was extremely symmetrical. So you could actually solve the equations. You could write down the solution on a piece of paper. And that's the Schwarzschild solution for the empty space and the Friedmann solution for where the matter was. And so you could combine these two together and simply write it down on a piece of paper, what the equations were. But that was only possible because you assume exact spherical symmetry. So it's absolutely the same all the way around a sphere. So the collapse was exactly symmetrical. But the fact that it had no pressure, nothing to stop it, if you like, the falling in matter, and the fact that it was symmetrical means that where's it got to go? There's nothing to stop it, so it meets in the center. And so the density would become infinite at the center, and so you get this infinite density, singularity, where your equations give up because things go to infinity. And what do you do? So that was the problem. But most people thought, oh, well, that's not realistic because things will be swishing around in a complicated way. They won't meet in the middle. They won't be aimed at the middle. So what do you do? But I didn't try to solve the equations. That was hopeless. I didn't know much about how to program computers, and so that was hopeless. But I had my way of thinking, which is to see how light rays focus and how they behaved and what. It was actually, you see, there were two problems I'd worked on before, which were helpful to this. One is the one I described in my lecture, which had to do with the steady state model, which is one of the things that got me interested in doing cosmology and my friendship with Dennis Sharma, which was very important to me. The other was quite a different problem. I was working at the same time, a little bit earlier, in 1964, on a problem, a paper which I submitted to the Royal Society, which had to do with the asymptotic property of gravitational fields. So you're looking at gravitational radiation And how does it behave, and what does the curvature look like in detail as you go out to infinity? And I had a way of looking at this, which meant squashing down infinity to a finite boundary. So I have in my talk this picture of the Escher picture of the fish, and they've got this boundary, circle limit boundary at the edge. But that's a particular instance of what I was doing. We squash infinity down to make it look like a nice boundary. And I was able to prove certain things. But I had one little problem, was that I needed that infinity looked like a sphere. So this means that as you look out at the sky, you see the celestial sphere. Now, the opposite direction, when you're looking at the future infinity, does it necessarily have this structure of a sphere out there? Or could you have something more complicated? And so in the appendix to this paper, I thought any sensible person will just assume it's a sphere. Sure, why not? But I wasn't satisfied with that. So I thought about, well, can you prove it's a sphere? So I thought about what do light rays do when they get out? And I had a sort of argument. I think it was reasonably good in the appendix. It wasn't part of the main paper. I slaved it away, thinking I was wasting my time all the time. And I developed a lot of these techniques of looking like, what is the boundary of a future of a, you look at a point, you look at its future, and what's the boundary look like? And how do the light rays cross over? And you don't look at that part after they've crossed, you just look at the outer boundary and what does that behave like, and so on. And I developed enough of an understanding there that when I looked shortly afterwards, not very long afterwards, at this problem of gravitational collapse, and I knew about the Lifshitz-Kalatnikov paper, which seemed to show that you didn't get singularities, and I wasn't totally persuaded by that. And I remember walking in the woods and trying to think of what condition could you have to show that these singularities, I don't know why, I pretty well thought that the singularities were generic. I guess that was an intuition I had. I don't quite know why. I was toying with both ideas, that it might bounce out or it might be generally singular, but I think I thought it was probably generally singular, in opposition to what the Russians seem to believe. And but I realized you needed something non-local. Just a local condition that says things blow up because of the equation wouldn't work. Just because of the symmetry, you could blow everything up, and there's nothing of the scale to tell you that it could be local. So I was pretty persuaded it had to be something more global, the condition which was sort of more global. And then it was later on, and this story I keep telling people about, I think I had this lectureship at Wadham College in London, and I think I was going to my office in the neighborhood in London there, near Euston Square, and I was talking to a colleague who was an Englishman called Ivor Robinson. He actually his job was then in the US, but he was a very good person. He was one of these people very skilled at producing exact solutions. He had a real skill at doing that. I don't know what he was talking to me about. He was also skilled with verbal. And if you talk to him, he would talk in this wonderful way. The Americans loved him because he had this flowery way of talking in English. It was a beautiful skill. And so he was talking to me like this. He was doing most of the talking. And then we got to this point where we crossed the street. And as we crossed the road, he stopped talking. And we were looking at the traffic. See? And then we got to the other side, and then he talked again like this. And then after he left, I had this strange feeling of elation. And I couldn't think, what on earth is this? I must have had something during the course of the day that had cheered me up. And so I'm rather fussy about this sort of thing. So I went right through, starting from the beginning, and what did I have for breakfast, and then what during the day, and this, no, I can't do that. And then it came to me crossing the street. My God, that was it. I had this idea as we crossed the street of a characterization of a point of no return, which was a sort of global characterization, which is a thing I called a trapped surface. And this was a surface which, you see, as the matter falls inwards, you surround it. You're still now probably in the vacuum region outside the matter as it collapses in, and you can draw the sphere around it. And it has a curious property that if you had a flash of light, imagine an instantaneous flash of light on that sphere, that the light rays converge both ways. So if you imagine a convex surface, imagine a flash of light on that surface. On the concave side, the light rays will converge. On the convex side, they will diverge. Well, on this trapped surface, they converge on both sides. Now, actually, it sounds strange, but there's nothing wrong with that if it's only a local region. What's wrong with it is when it goes all the way around the sphere and it's converging all the way around. And I call that a trapped surface. And I realized from what I'd been doing on this other problem, that I knew if you looked at the future of that region, that it had to have a boundary that was what's called compact, closed up on itself because of this focusing. And then you could see that was inconsistent with the initial surface being non-compact. So you could prove a theorem. I didn't have the best way of doing it at that time. There was a slightly better way that Charles Misner, who I learned a lot from in Princeton, and certainly a lot of things to do with the collapse. You see, one thing that I remember him telling me about was, again, this question of whether it's a local. You see, one of the things that people worried about was when stars collapse. You see, there's a lot of work. I think Dennis Lemkol in his talk talked about this, the history of the collapse of black holes. And a lot of this work was on stars. And when they collapse down to this, what's called the Schwarzschild radius, the density could be enormous. And so you might say, well, we don't really know enough about densities, and so maybe that's the problem. But you see, what Charlie Misner persuading that's nothing to do with it. You've got a big system with lots of stars coming together, and the overall density of those stars coming together can be very small, much less than the density of air, and you would still get this condition of a trapped surface.
Did this take you to working with Stephen Hawking?
It did.
And what happened in that collaboration?
Well, you see, it was, I think it was probably December '64. I gave a talk on this. I just thought of this idea with the trapped surface, and I'm not sure whether I'd actually written the paper or not at that point. I think perhaps I had, but I gave a talk at King's College, London, at which the distinguished physicist, the relativist J.L. Singh, whom I learned a lot from. He had a very geometrical way of thinking about relativity, and I learned a lot from his books on that. But he happened to be in the audience, which I was very proud of. And I gave this talk on my singularity theorem, which was the one that eventually got the Nobel Prize. I gave a talk about that. According to the film, Stephen Hawking was there with sparks coming out of his head from being inspired by this talk. He wasn't there at all. That was just fabrication. But Dennis Sharma, who was in Cambridge at the time, and he heard about this talk, and he said, well, would you like to come and give a talk, a repeat of your talk in Cambridge? And that was perhaps January in 1965, and I gave a talk there. And Stephen Hawking was in the audience, and Dennis was very keen that I would get to talk to Stephen. So he organized a private session that I had with Stephen and George Ellis, who was collaborating with Stephen on trying to find some sort of a theorem about on the Big Bang, but it was much more limited and using techniques that weren't the kind I was using. So I gave a little private talk to them on my techniques. Stephen very quickly picked up on the techniques and used my theorem in a reverse time direction in the remote, very distant. So it wasn't quite so, well, the argument was to show that my theorem could be used in the reverse time direction to show that the singularity of the Big Bang was generic too. So you could imagine a situation where the Big Bang was not the beginning, but there was a previous collapsing universe, and this swished around and did something complicated and then came swirling out again. And that's what the Big Bang was, you see. So I think that was quite a picture that was presented by people. I don't remember.
That came out of you and Stephen Hawking working together, did it?
I can't remember whether that was a prevailing view that people had. But you see, that was what Stephen worked on, yes. I mean, he was using the techniques which I'd used for the black hole collapse, but as applied to the whole universe, but now in the reverse direction. He then developed these techniques much further than I had. He he used them and introduced other ideas, which, you see, I had a condition that, to describe it properly, we're being a little technical, but it's more or less saying that you can have an initial moment, if you like, where you know what's going on in space-time, and then you can evolve your equations into the future. Now, that's what's called a Cauchy surface, because the famous mathematician and philosopher Cauchy had this view that you could, well, I guess that was a pass. But Cauchy was using the idea of developing equations into the future, and when can you do that, you see? So we call this a Cauchy surface. It's very appropriate. He considered these things. So that's the surface that you start from. When I say it's a surface, it's a three-dimensional space, a surface in space-time. So it's a moment in time, if you like. And that Cauchy surface, its evolution then gives you what happens in the universe. Now, might it be like that, or it might be that some other thing comes and joins onto your universe, you see? So you have to consider those other possibilities. And so Stephen developed ideas of what he called Cauchy horizons, which are a very important idea, coming from extending the things I did by quite a lot. And then later on, we got together. There's a curious story on there too. We got together and wrote a paper together, which generalized pretty well all the techniques we'd had previously into one theorem.
Can I take you back to the Big Bang? They're saying that the Big Bang didn't start from nothing. It eased in the previous universe.
Well, that was an idea.
And can you develop that? Because that's fascinating. So there was a previous universe before ours. Was there a previous universe before that previous universe? And does it?
I think we shouldn't take this as a theory at the moment. I think it was more that people did. I mean, yes, there were certainly people who discussed that kind of thing.
What evidence is there for it?
Sorry?
What evidence is there for this previous universe?
No, none whatsoever. No, you see, it was more. I mean, there is now, but that's jumping ahead. At that time, there was none whatsoever. It was just, you see, there's wild speculations. People were wildly speculating about all sorts of things, you see. Yes, you see, that Einstein had this wonderful theory, and people, this was a wonderful playground for making cosmologies, you see. And this was what people were doing. When I say people, there were a lot of mathematicians who maybe didn't know much cosmology or physics, or maybe they were cosmologists who were trying to see what the universe might be like. I mean, is it a simple model? You see, Schwarzschild produced this early solution, which is the thing which described Oppenheimer and Snyder used, and so on. And the initial models of spherical symmetrical black holes came from that. But there were also people working on cosmology. There was this Russian mathematical physicist called Friedman, and Friedman had discussed various different kinds of global structures. The universe might be spatially closed, it might be spatially flat, it might be spatially hyperbolic. That's the kind of geometry that in my Escher picture I showed you. So these were all possibilities that people considered. And it might be there was a Big Bang, or maybe you could have a solution which didn't have a Big Bang in it, or maybe other things. There are all kinds of things. In the steady state model, you didn't have a Big Bang. And so certainly there was a lot of discussion about different things that could happen. And the point about the work that Stephen was doing there was it narrowed these down, that any of those models in which you had an initial collapse, which bounced to an expansion, and certainly you could have Friedman-type models which behaved that way, whether people took them seriously. I mean, there was one which was called the oscillating model. It was spatially closed, and it bounced like this. It had infinite number of repetitions. It was quite a well-known and studied model. And so maybe something like that was true of the universe.
So where are you in your thinking about it then? Do you think there was a previous universe to the one in which we, let's call it inhabit to inflation?
I have to think of the history here, because initially, you see, when I went to Cambridge and I got involved with Danish Sharman people, and they were all very keen on the steady state model. And so I got quite keen on that. It wasn't philosophically very nice because the universe was there all the time, and it was there and there and there, you see. And so it was philosophically satisfying. And I felt that too. But then when the Penzias and Wilson really discovered that there was this Big Bang and evidence for an early stage of the universe in which it was extremely hot, and a microwave background, which was discovered, seemed to indicate that there was this early stage, and that really put paid to the steady state model. And I greatly respected Dennis, because when he was convinced that this was true, he says, look, I was wrong. And he went around lecturing and saying, look, now take the Big Bang seriously. There really was this initial stage where you might have to consider quantum gravity and all these things like that. Yeah, that was all going on. But you see, Stephen was really arguing against the possibility of a previous collapse bouncing into a expansion. And that was it. You could use the theorems in future directions and maybe strengthening my black hole result by maybe getting rid of the Cauchy surface condition. And sure, you could do things like that. But I think he was primarily concerned with proving that there was a Big Bang. Yes.
We've gone over our time, but they said it didn't matter, so I'm going to keep going on. They can trim it in brilliantly later. There's 2 or 3 questions. One is, as we're talking about beginnings, Big Bangs, you've described yourself as an atheist, but you've also said, I quote, I think I would say that the universe has a purpose. It's not there somehow by chance.
Yes, it's a bit difficult to interpret what I was saying there. I certainly didn't believe that there was some old man with a beard who waved his wand and produced our universe, or anything like that. A conscious being producing it, that didn't help at all. I mean, where did that come from, and so on? No, I didn't believe any of that. But there is something in the connection with mathematics, which is so deep in physics. The more one probes reality, the more one sees how tied up it is with mathematics. But it's not a kind of thing that you see. I guess it may have to do with my views on consciousness, and that there is something in the type of mathematics that's involved. We haven't really seen it yet in our physical theories, but we have to probe that kind of mathematics to understand what it is that governs conscious beings and things which go beyond computation and things like that. When I call it a purpose, I suppose I would say that in order to be a self-respecting universe, the thing which you might call a universe has to have beings in it that can perceive it. And it's something like that, if I could try and expand upon what I was saying. So it's not the purpose is to produce conscious beings, if you like. Maybe I could say it that way. But it's in a certain sense that it wouldn't even be a universe if there weren't conscious beings in it. Because otherwise there's been nobody to see it, if you like. I don't know, it's a little bit contorted argument.
Talking about, coming to this, talking about the about consciousness, there's a discussion going on, or a disagreement going on, about the connection, about the connection between fundamental physics and the human consciousness. On one hand, thinkers like Minsky believe that humans are machines, and there are a lot of people who gather around his case. You're in a minority, as I understand it. You say that physics are inadequate to explain the problem of consciousness. Could you give us some idea of the battle that's going on there?
You see, again, a lot of these things go back to when I was a graduate student. And I certainly, an important thing was, I think I was a graduate student, I went to lectures on general relativity by Bondi and by Dirac on quantum mechanics, and a course by a man called Steen on mathematical logic, Steen, S-T-E-E-N. And he explained Gödel's theorem. And I found it completely stunning, because what he said was, if you have this system of proving results in mathematics, it's called a formal system, and you could put this in the language of computers. You say, if you could put this formal procedure on a computer, and he talked about Turing machines and all that, so I learned about all that. If you could put it on a computer, then all the things you could see. How do you know what's true in mathematics? Well, you have a proof. And what is a proof? Well, you follow certain rules, axioms and rules of procedure, perhaps. And then if you follow them correctly, that's a proof. Now, what Gödel showed was that there are certain statements that you can't prove this way. But that's not so much what struck me. What struck me was that you could see by the way that Gödel constructed that the particular statement he produced is true. Now, how do you see it's true? You see it's true by virtue of your belief in the formal procedures that you're following. If you're simply following these procedures, why do you trust them? Why do you know that gives you truths? Well, you understand them. Now, if you understand them, then you know not just things that you can get using them, but things that you can get using your knowledge that they're correct. And that was remarkable. That's what Gödel's theorem does. It uses your belief that these procedures give you truths, and that gives you a truth beyond the procedures.
Is it like faith?
I wouldn't say so. It's like understanding. You see, faith,
a lot of times, but never mind.
faith is a word. You see, you're sort of given this thing, and you follow it.
I interrupted.
No, and it's a good question. It's not. That's exactly what it's not like. You see, it's like understand. You understand something. Now, I thought, what does this tell us? It tells us that understanding is not computational. It's not a computation. And understanding is something you do with your consciousness. So consciousness is, it's part of consciousness as understanding. And it's that part of consciousness which is enabling you to do something which transcends a computation. And that's a view I hold, and nobody has really attacked. I mean, lots of complaints people have made endlessly, but the argument which one can produce, it's not quite the argument which I tended to concentrate on because I got myself all wrapped up in complications. There's a much simpler argument, but it's quite clear. I was going to say it's quite clear to me, and I don't know why people don't follow me very much, that understanding, and Gödel shows you this, that understanding is something which is not a computation. And that thing is what consciousness is doing. Okay, you can make these machines which play Go incredibly well or chess or something, but they don't understand a damn thing. They don't understand anything. They've just, either they've played itself a zillion times and it's maybe pattern recognition or goodness and so on. It doesn't understand why such and such a thing works. And it's that thing which is not encapsulated without understanding.
Why do you think that your position is a minority position in this argument? But the idea that we can be analyzed like machines, provided we keep at it, as it were, is being accepted by an awful lot of people, as I understand it.
I quite understand why it's a minority position, because it means going beyond current physics. You see, you could put, I mean, I had this view already when I was a graduate student. It goes beyond Newtonian mechanics. It goes above special relativity. It goes beyond general relativity. You can put that on a computer. You see these things at LIGO, how you get these wonderful simulations. Yes, 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 yes. What about quantum mechanics? Schrödinger equation. That's computational. But what about the amazing thing that I was staring out of the window when Dirac came to it in his first lecture? Why is it that you can't have a piece of chalk in two places at once? I didn't follow his reasoning because I wasn't listening. Then I realized it's probably I couldn't have, because there isn't a reason. That's where you have to go beyond quantum mechanics. So you see, it's a very outrageous thing I'm saying. I'm saying that what is going on in our brains, which is making us conscious, is going beyond current physics. It's not outside physics, it's outside current physics. And it's what happens. This is the position I held then and still hold, is that it's what's involved in the collapse of the wave function. Now, the collapse of the wave function is something which people brush under the carpet when they do quantum mechanics. Schrödinger drove himself almost mad by trying to understand how that can make sense. And he was saying, you know, you wish it had nothing to do with quantum mechanics if I hadn't been, you know, if you'd understood all this jumping that has to go on, you see. The jumping is you follow the Schrödinger equation, and then suddenly it jumps. It does something. It does this or this or this. That's not following the Schrödinger equation. That's what's called the collapse of the wave function. We need a theory of the collapse of the wave function. When we have this theory, or when we know how to harness theory, then maybe we can make a conscious thing. I hope I'm not alive when this happens. I'm not sure I'm in any danger of that being the case, but it's sure, it's part of physics. It's not part of current physics. It's not part of computational physics.
Why do you hope you're not alive?
I don't know. I think there's something rather awful about it. I don't know why. I think if it was there, I'd change my mind. Say yes. I'd shake its hand and say, "Nice to meet you." Sure, but there is something rather frightening about it. I think, isn't there? Do you think
about the machine, the idea of human beings
actually being conscious?
Machines, yeah.
You see, I don't think any of these machines have any consciousness whatsoever. It's not even a tiny bit. It's just nothing, because they don't incorporate this thing which they need to incorporate. Now, if they built a device, let's not call it a machine, a device which could take advantage of, it could harness the collapse of the wave function, or what really is going on in the collapse of the wave function, then there is the potential for it to make a device which is conscious. And I certainly would accept that. They're not going to do it with computers. They're not going to do it with quantum computers. Quantum computer doesn't harness the collapse of the wave function. So sure, it's got to be something else. But no, people who will be around when these things come along will be quite happy to say, shake its hand and say, yes, okay, you take over, you're better than I am. That's all right. I have I don't mind things being better than I am, but I don't want them to claim to be conscious when they're not. That's all.
That's a wonderful place to stop. Thank you very much, Roger. That was terrific. Thank you very much indeed.
Very, very much pleasure.
Very generous in your explanations. Thank you.
Thank you.